Okay, so in the last section we talked about the very basics of units. What are dimensions? What are some of the typical units that are associated with those dimensions? And how do you change from one system of units to another? In this section, we're going to start really thinking about estimating things in the world around us in a quantitative way, right? So kind of getting into that mindset that the world around us is just waiting for us to think about it in a quantitative sense, right? So before I talk in detail about a technique for estimating things called Fermi estimation, let me just very quickly review scientific notation, right? So scientific notation, in case you have not seen this before, notation. So the thing that scientific notation is meant to address is this idea that as we go about, interacting with the world and also thinking about the world, we see numbers that have very disparate scales in them, right? So on the one hand, we might want to talk about, the size or maybe say the mass of a proton, and the mass of a proton is like 0.00000000000000000. There's a lot of zeros before you finally get to some numbers. If you have, say, if you want to write this in, say, in terms of kilograms, right? And wasting all of this ink and spending all of this time writing down all of these zeros is just completely impractical. It's also kind of error prone, and it obscures kind of, how different is this very small number from any other very small number, right? So at the same time that we want to think about very small numbers, we also want to think about very big numbers, right? So to take a non-physical example, you might say, how much does the US government spend every year, right? So let's say spending US government in 2018, you can look up on the CBO's website that this was about, 4,109,042,000,000, right? And the point is, in the English language, we have specialized words that help us deal with situations like this, right? So rather than writing out this whole mess every time, we just say, oh, this is about $4.1 trillion. And the idea here is that we have a specialized word, trillion, that tells us, right off the bat, how big is this number really, right? And so the idea of scientific notation is just to systematize this kind of colloquial English sense of describing very big and very small numbers by breaking things down into a prefactor and a power of 10, right? So I might say $4.1 trillion. Well, that's the number 4.1 times 10 to the power of 12, right? Dollars. And similarly, this mass of a proton, rather than writing out all of this terrible bunch of zeros, I can just say, well, that's about 1.67 times 10 to the minus 27 kilograms, right? And so, this kind of notation comes in really handy because the exponent on the power of 10, this minus 27, that is really an immediate indication of how big something is. Or how small something is in this case. And if you want more details, you look at the number sitting out in front, right? And, right, so it's great. So it kind of solves this problem of, well, this is a poor communication strategy, just writing out a bunch of zeros, and it makes things very easy to compare, right? So this introduces us to this idea of an order of magnitude. And colloquially, this is just a way of saying, approximately how big is something. And in this class, if I'm talking about an order of magnitude, I'm basically referring to what is the exponent sitting out in front of on top of the 10 here, right? And indeed, as we go about our lives and we quantitatively think about the world around us, often the order of magnitude of some quantity is a lot more important than the precise number. If I see a car and I'm in the middle of the street and I'm about to get hit, I don't really care if it's going at 23 miles an hour or 24 miles an hour. But I definitely want to know if it's going at 2 miles an hour or 20 miles an hour or 200 miles an hour. The kind of range of outcomes for me are extremely different in those three scenarios. And the order of magnitude tells us what we want to know, right? Great. So, again, just as a quick math note, just in case it's been a little while since you thought about how these exponents work, something that we'll be, using a lot is that if you have a product, say, 10 to some power, multiplied by 10 to some other power, so 10 to the x times 10 to the y. Remember that you get the answer by saying that's 10 to the x minus y, or x plus y, sorry. And if I was dividing, it would be x minus y. so on and so forth. Okay, so that's great. So let's think about using scientific notation then to make what are often called order of magnitude estimates of various, quantitative questions out in the world. So for instance, here, let me pull up a picture. Fantastic. This is a photograph from the Washington Monument of a presidential inauguration that took place some time ago. And suppose you wanted to estimate the number of people in this crowd of folks, right? Now, certainly, even if you could, you're not going to zoom in on this image and really try to pick out and count individual people amongst this mess of pixels. But you also don't really care, what the exact number of people is. You want to have, an approximate order of magnitude sense, just about how big is this crowd, right? And let me go through this example and then kind of talk about the general strategy. And then I'll give you another kind of more complicated example of applying that general strategy to a problem at hand, right? So I have this photograph. Maybe I'll pull it back up in just a second. So let's say estimating crowds. Estimating crowds in a photo. Okay, so one strategy for estimating how many people there were in that photograph would be something like, well, let me try to estimate how dense the dense parts of the crowd were, and then let me also try to estimate how much of the surface area of the ground in that photograph was occupied by dense crowds, and then we might imagine multiplying those numbers together. So our idea is to separately estimate the crowd density. And here, I mean people per, say, amount of area, not volume, since they're not stacked up into the air. So we'll estimate the crowd density and fraction of area. Fraction of the National Mall that's covered. And before I start giving numbers, maybe this is a great time for you to pause this video and if I just bring this crowd up in front, how might you go about estimating those different numbers, right? So maybe pause the video, sit down with a piece of paper, and, without looking up the answer on Google, try to guess how many people are in this photo. Okay. Fantastic. Now that we're back, or perhaps you never left, that's disappointing, let's go through these two things that we want to estimate one by one, right? So one, density. I don't really know what the density of that crowd is. But certainly when I zoomed in on, the pixels in that image, people looked like they were pretty close together. How close? I don't really know. It's like they were definitely more than inches apart in general, but they were definitely less than meters apart, right? So people are occupying something in the space, in between the scale of tens of centimeters and a meter, right? So one thing that we can do, and you'll see why I picked this particular number when I talk about the general strategy, is to say, let's imagine that each person is occupies, about 1/4 of a meter squared, right? So, that seems reasonable. There's not quite a foot of space in between people in those dense crowds. That seems reasonable, right? And then you might say, okay, fraction of National Mall, where that crowd gathered, covered by these dense crowds, right? So we kind of look at this photograph again. We say, oh, well, the National Mall is this whole space in between the buildings. I've got big blobs of crowds all over the place. Maybe they're slightly smaller up here. They're taking up a lot of area around here. I don't know, but we just want an order of magnitude estimate here. So density, fraction of National Mall. So let's just say about a half, maybe about a half of the area of the National Mall is covered by people. Okay, and I guess the thing that we still have to know to put all of these pieces together is, how big is the National Mall? How big is the National Mall? Great question. This is obviously something you could look up, or maybe you already know. One way of estimating it is, maybe you've traveled there. I've been there. I remember it took I don't know, something like 40 minutes to walk from one end of it all the way to the other end of it. So it feels like it's about 2 miles long. If I look at that photograph, sorry, I just pulled up the wrong picture. If I look at that photograph, the space horizontally, it's maybe like 2 soccer fields in my imagination. So you can kind of put those estimates together and get an approximate value for the surface area of the National Mall. You could also say, well, I actually happen to know how big it is. It's about 146 acres. And I also know that, because I want to convert these units into each other, an acre is kind of like 2 soccer fields, if I think of a soccer field as about 100 meters by about 80 meters. So now, and I say 1 acre is about 4,000 meters squared, half of 100 times 80. And now I can put these numbers together. I can say, oh, well, I've got, so people in crowd. I've got, on the one hand, an estimate that says I have about 1 person for every quarter of a square meter. So I'll write that as 0.25 meters squared. I say how much of the surface area of the National Mall is covered in people, and I said it was about a half. So I'll say that's 146 acres divided by 2, right? And I want to get units to agree. Here I've got meters squared, here I've got acres. So I'll multiply this by about 4,000 meters squared per acre. Again, just using our trick of multiplying by 1, but writing 1 in some clever way. And I finally go ahead and pull out a calculator or just type this sequence of numbers into Google or whatever, and I find out that my estimate for the number of people in the crowd is about 1.1 times 10 to the 6, right? People. Great. It's about 1 million people. We could easily be wrong in the precise number. Do I trust, that this is 1.10? Absolutely not. Do I trust this first, digit after the decimal point? Not really. In this style of order of magnitude estimation, you can easily be off by a factor of 2, but the point is you're probably not off by a factor of 10. And the great thing about this style of work is that it's a very fast way to make rough, approximate guesses that can inform your understanding of a situation. And the beauty is you can always go back and refine your assumptions if you need to get more and more accurate estimates. So for instance, you can question any of these assumptions. I said people occupied about half of the available space. Well, you could try to, kind of measure the sizes of these rectangles. How much space are people occupying? You would need to know, I used the area of the full National Mall, but this doesn't have people in the photograph in between the Lincoln and Washington monuments, so you need to get another satellite photo, but you could refine that estimate. You could also say, is this density of people in the crowd a reasonable density? And you could either maybe, zoom in on part of this and try to get a better just approximation for the density, or you could look up studies of typical crowds to get, a better sense. And the point is that, again, it's an incredibly fast, easy way that you can practice to kind of start bringing a quantitative perspective to bear on the world. If someone tells you a number, you can very quickly ask yourself, well, does the order of magnitude of that number even make sense? And how does that compare to other orders of magnitude that are relevant for that situation? So for instance, in class, I think we'll probably go through the example of waste in the SNAP program as this kind of example. Okay, so fantastic. So this was an example of kind of putting together an intuition about, basic things we understand about the world, together with, making very rough estimates of numbers and using some unit conversions to start getting a handle on, at first a seemingly very difficult question. How many people were there in that crowd? It's a priori not a particularly easy thing to estimate. Right. So very good. So what I want to talk about now is kind of the general strategy that is often very effective in approaching these kind of problems, and it's called often Fermi estimation, or these problems are sometimes called Fermi problems, after Enrico Fermi, an Italian-American physicist, very prominent in the 20th century. So Fermi estimation. Okay, so in this class of problems, the goal is to get an order of magnitude sense of the quantitative nature of the answer to some question that we have. And it's often in the setting where a priori, it would be hard to just directly guess, and often we have no, easy data to work with, right? So no one's made a measurement for us. We have to kind of put together all of the pieces that we need. And there's many examples of this type of thinking, and depending on what field you're in, sometimes they have kind of the feel of interview style questions that are meant to test your general reasoning skills. How many golf balls could fit in an airplane? How many soccer balls can fit in a school bus? How many grains of sand are there on the earth? How many window washers are there in New York? This kind of thing. These are all great types of questions, I think, to practice on, because what they force us to do is start with a question and really break it down, reason about it quantitatively, and make an estimate, again, not about the precise answer, but about kind of a relative frame of reference of what the answer basically has to be. And then later on, if you go to the trouble of actually making a precise and difficult calculation, you can use your original guess to say, well, does my answer make sense? Or is it way off and I must have made a mistake? Or is it way off and there was something wrong about my original assumptions for the problem? And either way, you've learned something really important, either about the world or about the way you think about the world. Okay, so there's kind of a very, I think, systematic method that you can use to approach this class of problems. Okay, so systematic method. And I'll break it down into a bunch of steps, right? And then when I go through a case study in the next video, I'll do a one-to-one map of these steps to the problem we're thinking about. Okay, so step one is really, what can we assume? What can we assume about the problem? What can we assume about the problem? What information do we need? What info do we have? What do we need? And can we, importantly, break the problem down into smaller subproblems? Can we break down into subproblems? So for instance, in the crowd example, I said, well, just guessing the number of people in the crowd, that's really hard. But I can break it down into, well, can I guess the density? And if that's what I'm going to guess, I need things like, well, how much area is in the National Mall? I can either know that or look it up or guess it. And I need to come up with a guess of how much area in the National Mall was actually covered by dense crowd, right? So we broke the problem down into people equals a surface density times a surface area times a fraction of space occupied. Okay, so we think about the problem critically and we try to break it down into small component pieces that are each easier to reason about. Okay, and now we ask, step one gives us factors. Like crowd density, surface area, this kind of thing. And step two is, how big are they? Come up with estimates for them. How big are they? Okay, and maybe you've broken down the problem so that this is easier for you to answer. But a subproblem here is, what if you don't know? You've broken it down into something that's kind of as elemental as you can think of. What if you can't easily estimate? And here's an incredibly powerful trick for coming up with often very sensible guesses to numbers that you kind of have a very poor sense of. What you do is, underestimate the problem. So step one, come up with something that's a guess that is too small, right? And step two is to overestimate whatever the quantity is. Come up with another guess that has to be too big, okay? And then take the geometric average or the geometric mean, okay? Geometric mean. And what does this mean? So if I call my underestimate of some quantity, x, and I call my overestimate of some quantity y, the geometric mean is the square root of x times y. Okay? It's kind of like taking a normal average of numbers, but in this kind of geometric sense rather than in an additive sense. Why do you want to do this? Note that taking the geometric average is like averaging the orders of magnitude of your estimates. So if you have the square root of, say, 10 to the minus 3 times 10 to the 7th, that's the square root of 10 to the 7 minus 3. So that's 10 to the 7 minus 3 divided by 2, better known as 10 to the 2. And so you'll notice that this geometric mean is like taking the average of these two numbers, these two exponents, and taking 10 to that power. So the geometric mean averages your most underestimating order of magnitude guess and your most overestimating order of magnitude guess. And you do this instead of normal averaging, because normal averaging weights things too much towards your biggest guess. As a subnote, notice that if you did 10 to the 7 plus 10 to the minus 3 divided by 2, this would be like the normal average. So a normal mean would be this operation. And this is, 10 to the 7, that's a huge number. 10 to the 3, that's insignificant. This is basically the same as just writing down 10 to the 7 over 2. So it's completely ignoring, some of the information you have about the problem. This could have been 10 to the minus 3, 10 to the minus a billion, 10 to the 1. This normal mean wouldn't be able to tell the difference. The geometric mean kind of takes into account both your underestimate and your overestimate. I want to point out that actually this geometric mean trick was exactly what I did when I was trying to estimate the crowd density in the above problem. For example, I said, my underestimate, I know people are more than a few inches apart, and a few inches, that's like about 10 centimeters, so that's 0.1 meters. My overestimate, I guess this is under and overestimates of the space in between people, that's fine. My overestimate, well, I said, I know they're less than a meter apart, so my overestimate is 1.0 meters. And so my estimate of the whole crowd density was one person per square root of, 0.1 meters times 1.0 meters, all squared. Where the square is outside the square root, okay? And so, the geometric mean of these two numbers, that's about one person per 0.316 meters squared, which, in the example above, I just rounded that to something that was, a little bit easier to do the arithmetic on, one person per quarter of a meter squared, 0.25. But there's no reason that I, picked 0.25 rather than this, other than just convenience, And that's the kind of thing that I mean when I say, how much do I trust these precise digits? Not that much. But I know that my answers aren't going to be off by more than a factor of 2 or something, okay? So again, the point here in this example is that to the accuracy of these calculations, this type of rounding just doesn't matter. And so you should feel free to do things that kind of simplify your calculation. The important thing was making these underestimates and overestimates and finding a geometric mean to guess a reasonable scale for, in this case, the crowd density. Okay, so that's step 2. We're basically home free because we've broken down the problem into a bunch of factors, and we've either been able to guess what all of those factors are, or we have this geometric mean trick for coming up with some estimate of them. So then, step 3 is just combine your factors. Multiply them all together. And come up with an order of magnitude estimate, into order of magnitude estimate. Okay, and you should feel free to round. Feel free to round. Use scientific notation, etc. And this step was up here trivial. I estimated those 3 factors, I multiplied them together, and I got some number. Okay? So that's step 3. There's a few more steps because actually once you've arrived at your answer, you're not done. You need to interpret it, and you need to think about it. Interpret your answer. Interpret your answer. Compare it with what you know about the world. Did you get something that feels sensible? Compare it with the answers that other people trying to make the same estimate got, If you got a very different answer than somebody else, why did you get a different answer? Is it because you made a different assumption? Like you broke the problem down into a different set of factors in step 1? Or did you, use the same set of factors as somebody else, but you made very different estimates about how big they are, So think about your answer, compare it to what you know about the world, and ask yourself, if it's reasonable. And then step 5 is, this is science. This is the scientific process. You refine every step until you're satisfied with the quality of the assumptions you've made. You've made estimates that are as accurate as you want to be about the problem, so on and so forth. And so, for instance, in the crowd problem, I said, if I wanted to, I could go back and say, take this number, compare it to official estimates that were generated at the time that photo was taken. And I also identified, well, how could I go back and more precisely estimate all of these different features? How could I, if I needed to, come up with a better density estimate? How could I come up with a better coverage estimate? How could I come up with a better estimate of, 146 acres, but that also takes into account that big reflecting pool, right? People weren't standing on that, so, I need to refine this step a little bit. Okay. So, this set of steps, I hope, seems doable. It can be daunting, I think, to try to, just suddenly try to guess some of the things that I was referencing above. You have this method, but okay, how many grains of sand on all of the beaches in the world are there? How many molecules of water are there? I don't know. How far do you need to drive a car before one molecule thick layer of tire has been worn off by the road? It can be daunting to suddenly apply this method to these problems, but it's definitely something where the more practice you get, the better and better you'll be. Great. And so in the next brief video, I'll go through a more complicated case study where actually I don't even know how to look up the answer. And we'll see these kind of steps in action.